Neural face rigging, a novel paradigm in facial animation and retargeting. Realistic facial animation is essential for creating believable characters in films, video games, virtual reality, and other interactive media. The human face conveys a vast array of emotions through subtle movements and expressions, making it one of the most challenging aspects of character animation. Capturing these intricacies requires sophisticated techniques that balance technical precision with artistic flexibility. Traditional facial rigging methods often involve manually creating blend shapes or setting up complex bone structures, which is time-consuming and demands significant expertise. These methods may struggle to generalize across different characters or capture the full spectrum of human expressions. The need for a more efficient and versatile approach has led researchers to explore the integration of deep learning techniques into facial animation workflows. Neural face rigging, NFR, is a novel framework that addresses the limitations of traditional methods by automating the rigging process using deep learning. NFR employs a deformation autoencoder that learns a compact and expressive representation of facial deformations. By training on a combination of linear 3D morphable models, 3DMM, and high-resolution 4D facial capture data, NFR retains human interpretable control parameters similar to the facial action coding system, FACS, enabling artists to maintain creative control. This paper presents several key contributions. First, it introduces a deep learning-based facial rigging framework that automates the rigging process while preserving artist-friendly controls. Second, it proposes a versatile system capable of handling various facial mesh types regardless of connectivity or expression differences. Third, the approach captures fine-grained facial expressions, enhancing the realism of animations. Finally, the paper provides experimental validation demonstrating the superiority of NFR over traditional linear rigging techniques in both qualitative and quantitative assessments. Traditional facial rigging involves creating a control structure that allows animators to manipulate a character's facial expressions. Common methods include blend shape rigging, where a set of predefined facial expressions are linearly combined to produce a range of expressions, and bone-based rigging, which uses a hierarchy of bones or joints to deform the facial mesh. These methods require significant manual effort and may not generalize well to different characters or capture the complexity of human expressions. FACS is a comprehensive framework that categorizes human facial movements by identifying individual muscle movements called action units, AUs. It provides a standardized language for describing facial expressions and has been widely adopted in both psychological research and computer graphics for creating expressive animations. Recent advancements in deep learning have opened new possibilities for facial animation. Neural networks have been used for tasks such as facial expression recognition, synthesis, and animation transfer. Autoencoders, in particular, have been effective in learning compact representations of high-dimensional data, making them suitable for modeling complex facial deformations. 3D-MMS are statistical models that represent facial shapes and textures derived from a dataset of 3D scans. They allow for the generation of new facial geometries by adjusting model parameters, providing a way to capture variations in identity and expression. While deep learning and 3D-MMS have advanced facial animation techniques, challenges remain. There is often a lack of artistic control, as some deep learning approaches act as black boxes, limiting the ability of artists to fine-tune animations. Generalization issues can arise, with models trained on specific datasets not performing well on unseen data with different mesh topologies. Additionally, capturing subtle expressions remains difficult, as existing methods may fail to encode the fine-grained details necessary for truly realistic animations. The core of the NFR framework is a deformation autoencoder designed to learn a latent representation of facial deformations. The autoencoder consists of an encoder that maps the input facial mesh to a low-dimensional latent space and a decoder that reconstructs the mesh from this latent representation. The architecture is carefully designed to balance expressiveness and interpretability. The encoder captures essential deformation features, while the decoder ensures that the reconstructed mesh adheres to the original topology and captures fine details. To train the autoencoder, NFR uses a hybrid dataset comprising linear 3D morphable models and high-resolution 4D facial capture sequences. The 3D MMS provide a baseline with interpretable parameters corresponding to fax action units, while the 4D facial capture data offer dynamic deformations and subtle nuances from real expressions. The training process involves minimizing reconstruction loss between the input and output meshes while enforcing regularization to maintain human interpretable latent variables. The combination of synthetic and real data allows the model to generalize across different expressions and identities. NFR preserves an expression space where each dimension corresponds to a meaningful facial movement, similar to fax action units. This design choice ensures that artists can intuitively manipulate the latent variables to achieve desired expressions without losing the benefits of the automated rigging process. While automation enhances efficiency, artistic input remains crucial for crafting expressive and character-specific animations. Animators often need to adjust expressions to fit a narrative context or stylize movements according to a character's personality. Balancing automated processes with artistic control is essential for maintaining the creative integrity of the animation. NFR's latent space aligns with human understandable parameters, allowing artists to modify expressions by adjusting fax-like controls. This enables intuitive adjustments, seamless combination of multiple expressions, and fine-tuning of animations to achieve the desired emotional impact. By providing controls that are familiar to animators, NFR integrates smoothly into existing workflows. Case studies demonstrate how NFR enables artists to enhance or suppress specific facial features, such as raising an eyebrow or widening a smile. Artists can create complex expressions by blending multiple action units and adjust the intensity of expressions dynamically over time. These capabilities showcase the system's flexibility and alignment with artistic workflows. NFR is designed to be mesh agnostic, meaning it can be applied to facial models with varying topologies and levels of detail. This versatility is achieved through the autoencoder's ability to learn deformation patterns that are not tied to specific mesh structures. As a result, NFR can handle high-resolution scans with detailed geometry, simplified meshes suitable for real-time applications, and stylized characters with non-human proportions. The framework's robustness is demonstrated through its consistent performance across diverse datasets. By not being constrained to a specific mesh topology, NFR reduces the need for dataset-specific tuning and broadens its applicability. This adaptability is crucial for practical applications where facial models may vary significantly between projects. Comparative studies show that NFR maintains consistent performance across diverse datasets, outperforming methods that struggle with different mesh types. In tests involving various characters and expressions, NFR produced more accurate and realistic animations compared to traditional techniques, highlighting its superiority in handling mesh diversity. Capturing subtle facial expressions, such as micro-expressions or slight muscle twitches, is challenging due to their transient nature and low amplitude. These details are essential for conveying genuine emotions and enhancing realism. Traditional methods often lack the resolution or expressive capacity to represent these fine-grained details accurately. NFR addresses this challenge by utilizing high-fidelity 4D capture data during training, exposing the model to a wide range of subtle deformations. The autoencoder is designed to retain high-frequency details by minimizing loss functions that emphasize fine-grained features. Additionally, the integration of real-world data ensures that the model learns from authentic expressions, enhancing its ability to reproduce them. By effectively capturing and reproducing subtle expressions, NFR enhances the believability of animated characters. Viewers are more likely to perceive the animations as lifelike, which is particularly important in applications like virtual assistants, digital avatars, and cinematic productions. The improved realism contributes to a more immersive and emotionally engaging experience for the audience. Experiments were conducted using a workstation equipped with high-performance GPUs to handle the computational demands of training and inference. The software environment included deep learning frameworks such as TensorFlow or PyTorch. The implementation leveraged parallel processing capabilities to optimize performance. The training and testing datasets comprised both synthetic data from 3D MMS and real 4D facial capture sequences from publicly available datasets. Evaluation metrics included reconstruction error, expression accuracy, and user satisfaction ratings from professional animators. These metrics provided a comprehensive assessment of both the technical performance and practical usability of the NFR framework. Visual comparisons demonstrate that NFR produces facial animations with higher fidelity and more accurate expressions compared to traditional methods. The animations capture subtle movements, such as the wrinkling around the eyes during a smile or the slight asymmetry in natural expressions. These qualitative results highlight the effectiveness of NFR in enhancing the visual realism of facial animations. Statistical analyses show that NFR achieves lower reconstruction errors and higher expression accuracy scores. For example, NFR reduced the mean squared error by a significant margin compared to baseline methods. These quantitative results confirm the advantages of NFR in accurately modeling facial deformations. Professional animators evaluated the usability of NFR. Feedback indicated that the human interpretable controls were intuitive and integrated well with existing workflows. The automation reduced the time required for rigging without sacrificing artistic quality. The ability to adjust fine details was highly valued, suggesting that NFR effectively balances efficiency and creative control. Facial animation retargeting involves transferring expressions from one character to another, which can be challenging when the source and target have different facial structures. NFR facilitates retargeting by providing a common control framework based on facts-like parameters, allowing expressions to be mapped accurately between characters regardless of differences in mesh topology or proportions. Implementing controls familiar to animators enables a seamless retargeting process. Animators can adjust expressions using the same parameters across different characters, simplifying the workflow and ensuring consistency in the emotional portrayal. Examples of successful retargeting include transferring human expressions to stylized characters while preserving emotional intent, adapting facial performances captured from actors to digital avatars in virtual environments, and enabling cross-cultural expression mapping by accounting for variations in facial morphology. These applications highlight NFR's potential in various industries, including entertainment, virtual reality, and telecommunication. NFR offers several advantages. Automation reduces manual effort in rigging, allowing artists to focus on creative aspects. The system's versatility enables it to handle a wide range of mesh types and character designs. Its ability to capture fine-grained expressions enhances the believability of animations. Additionally, the preservation of human interpretable parameters allows for intuitive adjustments, contributing to a more efficient and flexible facial animation process. Despite its strengths, NFR has limitations. Training the autoencoder requires significant computational power and time, which may not be accessible to all practitioners. High-quality 4D capture data may be scarce or expensive to obtain, potentially limiting the diversity of training data. While robust, the model may still face challenges when encountering expressions or facial features not present in the training data, affecting generalization. As with any technology that manipulates human likenesses, ethical concerns arise. Unauthorized use of facial data could infringe on individual privacy rights. Advanced facial animation techniques could be misused to create deceptive content, such as deepfakes. Cultural sensitivity must be considered to respect differences in expressions and avoid reinforcing stereotypes. Addressing these concerns requires adherence to ethical guidelines and the development of policies regulating the use of such technologies. Potential improvements include optimizing the model for faster inference to enable real-time applications, incorporating transfer learning techniques to adapt to new characters with minimal additional training, and combining facial animation with speech synthesis and body gestures for holistic character animation. These enhancements would expand the capabilities and accessibility of NFR. NFR could be integrated with virtual reality, VR, and augmented reality, AR, to enhance the realism of avatars and interactive characters in immersive environments. Integration with motion capture systems could streamline the workflow for animators by directly applying captured performances to characters, reducing the need for manual adjustments. Beyond entertainment, NFR could be applied to education by creating interactive educational tools with expressive virtual tutors, healthcare by assisting in therapy for conditions affecting facial expressions such as autism spectrum disorders, and telepresence by improving remote communication through conveying nuanced facial cues via avatars. This paper introduced neural face rigging, a novel framework that automates the facial rigging process using deep learning while preserving artistic control through human interpretable parameters. By leveraging a deformation autoencoder trained on a combination of 3D morphable models and high-fidelity 4D capture data, NFR addresses the limitations of traditional methods. NFR represents a significant advancement in facial animation technology. It bridges the gap between automation and artistic flexibility, offering a tool that enhances efficiency without compromising quality. Its ability to handle various mesh types and capture fine-grained expressions opens new possibilities for animators and developers. As the demand for realistic and expressive digital characters grows, technologies like NFR will play a crucial role in shaping the future of animation. By continuing to refine these methods and addressing their limitations, the industry can move toward creating more immersive and emotionally engaging experiences.